All right, welcome. Let's talk about the basic ideas behind torque. All right, so this video describes the most basic ideas and definitions behind torque. There's an accompanying video which explains the right-hand rule for deeper understanding needed for the more complicated problems, but this will definitely be good enough for honors or regular physics. AP, you're going to have to decide on what your teacher does and what problems. AP Physics C, you would definitely benefit from the right-hand rule video. So we're just going to talk about what is torque, what does it mean, how can you draw vectors so you can figure out the angles for torque, and talk about the units for torque. All right, first of all, what is a torque? Well, if you think a torque is the rotational equivalent to force. So if you think of when a force is applied to something, it moves that something in a straight line. When a torque is applied to something, it rotates it. So let's take for example, let's take a door. Now, you may not really be thinking of a door as something that rotates, but yeah, when you open it, its hinge, the center of it, would be like the center of rotation. And if there were no walls and the hinge was a 360 hinge, you could swing that door, much like a revolving door, 360 degrees. So, here we have just a picture of an exaggerated hinge and a side door. And what I want to do is I want to look at the top view. So this top is what we're looking at. So it's called the bird's eye view. So this would be the hinge and this would be the door top. All right, so this is the example that we're going to use. Now, here is your basic torque equation. This is not a T, it's actually pretty fancy. It's a Greek letter called tau, and that stands for torque. R is the position vector. You usually draw R so that it's the butt of the vector, or the base of the tail of the vector, starts where the hinge starts, or starts at the center of rotation, and it goes in the direction of the object. Force is obviously the force that you are going to apply. Now, before you even took physics or whatever, just from living, how many years that you've been living on this earth, where would you push a door so that you could move it the easiest? Well, where are doorknobs located? Well, unless they're just there for show, like in these fancy big houses or whatever, where you might have your doorknobs in the middle, normally everyday usable doors, the doorknob is located at the edge of the door. Well, there's a reason for that. You want to make the torque, okay, so what you want to do is you want to use as little force as possible, but actually move or rotate the door. And this is what happens when you use a torque. So, so right now, how could we get the largest torque? Well, you can get the largest torque by having the largest position vector, sometimes called the moment arm or the lever, depending on your textbook. So a lever arm, the bigger this value, the bigger the torque, and the bigger the force, the bigger the torque. So if you think about it, if you were going to place a force right here, then your moment arm, if you were going to place a force right there, then your moment arm would only be that big, and you would not be getting as big a torque as you possibly could. That is why the closer to the edge of the door, the force is, your lever arm is bigger, and a bigger value here times a bigger value here equals a bigger value here. It's the same idea if you wanted to loosen, say, a lug nut from your tires. You get a flat tire and you have a lug nut. You have that tire iron, so that's the little thing that goes over the lug nut. And if it's short, okay, so I'm going to do my best. Here's like a little lug nut. And we have the thing here. If it's short, then what's happening? You have a little moment arm or a little lever to go with your force. But if you have a long, come on, do it. There we go. If you have a long lever arm, then your R is this big and your F is there, and so you could, if they're tightened really, really hard and you happen to be a small person, then you don't want to use, you can't use a lot of force, and so the bigger the moment arm or the lever arm, the less force you have to use. In fact, one of my friends, she was when she was in college, she was, well, she's kind of small, and her dad gave her an extension, so she had a tire iron that came with the car, and he actually had a metal piece that went over the end, and so this way it would give her this much extra distance, so she could use that much less force in order to get a lug nut off if she were in an emergency situation where she had a flat tire. In the last slide, we were kind of ignoring this cross sign, kind of pretending it was a multiplication sign, and it half is. A cross product, which is what R cross F or any of these cross products are called, are really vector products. So it's multiplying vectors. When you did work, now maybe if you are in honors or regular, you might not have stated this explicitly, but you did F dot D, that little dot, that means more than multiplication. That means scalar multiplication. So work was not a vector, but torque is a vector. So for a vector product or cross product, you are going to get a vector. All right. Now, this cross product is also equal to this. And don't be scared about phi. Phi is just another variable for an angle. You probably are familiar with theta. Well, now I don't know why a lot of books use phi when they talk about cross product. Phi is the angle between the force vector and the lever arm or the position vector. Now, when you're talking about a cross product, we are talking where we have the tails of both vectors kind of facing like this. So in a case, this is supposed to be a wrench, or you could think of it as a tire iron from the lug nut example. You put your position vector right here, right at the, I'm going to use red, right at the center of your rotation, and this would be your position vector. All right. Now, suppose that I am going to put a force at an angle like that. Okay. So I have two vectors, but if I want to find phi, the angle between them, all I would do is I would take this vector, I would take this vector and I would move it over here. So if I were going to do that, I'm just going to do a dotted line. It would go like this, which is what I drew right there. All right, and this would be phi. Now, a little trick here, because when I was learning cross products and that, I was always a little bit confused. Well, this kind of looks like the angle between the vector, and it is. But you know what? The beauty of it is this. If you put in your calculator two supplemental angles, by supplementary I mean that phi plus theta, it's a straight line here, right, would equal 180 degrees. So if you put in, I don't know, just say 40 degrees, oh, come on, that's right. Yeah, that's just being darn evil. I'll try another color. 40 degrees for this one, then this would have to be 140 degrees. 40 plus 140 equals 180. If you were to take the sine of 40 degrees, and I'm just picking these angles once again, and the sine of 140 degrees, you're going to get the same answer. Put it in your calculator. I'll wait. Put me on pause. All right, so hopefully you put me on pause and you proved it to yourself. So, because there's a lot of different ways when we start doing static equilibrium, there's a lot of ways that you could be looking at these vectors. So I'm trying to, it may seem like I'm making things more complicated right now, but really I am not. Your angle between the vectors, you could pick this one or this one. It doesn't matter. Your sine of each of those is equal to the same value. All right. But why is the cross product equal to the magnitude of r times the magnitude of f times the sine of phi? Well, the torque is the force that actually rotates the wrench or the tire iron, right? So if I were going to break this up into its components, I'm going to get this, and I'm going to get this. Okay? This, if this is F, then this is F, and it's adjacent to phi, so cosine of phi. And this is side is opposite to phi, so this is F sine of phi. Which of these forces actually causes the wrench or the tire iron to rotate? Would tugging on it in this direction help? No, that's not going to rotate it, is it? Would pushing up on it in this direction help? Yes, it would. So really, this is the only component of the force that is actually rotating the wrench around, which is why you could think of this expression as being written R and then F sine phi. You know what I mean, even though that writing is terrible. All right, so this is another way of looking at it. It doesn't explain everything why this goes to sine of theta, but now you get the idea that this is the only component of force that actually rotates the tire iron. All right. Now, the last thing about torque that I want to talk about on this slide is this guy. And how do you know what direction the torque is in? All right. So what you are going to do is you are going to use something called the right-hand rule, but we're going to, if you're in honors and regular physics junior year, you might not have to worry about the right-hand rule. But you would want to know which direction the torque went. So I am going to show you, hopefully, a nice, easy way to do that. So let's clean up this area just a little bit. All right. So, yikes. Okay, so if I were to draw okay, so this is my R, and this is my F. Okay. You know what? Let's go back to the wrench. I think that's easier. All right. If you were told that there is going to be a force on the wrench and it's going to be pulling that way, wouldn't you agree that the wrench is going to go in a counterclockwise direction? I think you would. So in most textbooks, so check with your teacher, check with your textbooks or whatever, but in most textbooks, counterclockwise means positive. So it would be a positive force, or a positive, so going in the positive direction, and it would be out of the page, which the right-hand rule would help you with. depending, so you're going to take the lead from your teacher as to what you need to know. If you, for example, had a wrench going like this, and you put a force this way on it, okay, your R would be this way. So we would have R. Come on, work with me here. I could move my R like that. R cross F. So it would be turning the wrench in a clockwise direction. R cross into F is clockwise. Clockwise is considered, the general rule is it's considered negative, and the torque would be going into the page. I cannot obviously show you my hand right now, so if you wanted to know why we're talking into the page, you need to listen to the right hand rule video. But like I said, if you're going to define torques clockwise, if the object turns clockwise, it's going to be negative. If it turns counterclockwise, it's going to be positive. Okay, I've told you a lot of different things. Let's piece them together and review. A torque is a force that causes something to rotate. The larger the lever arm, or the bigger the force, the bigger the torque. If your phi is, well, think about it, sine of what angle gives you the largest number? Sine of 90 degrees, right? If you had your R and you're pulling directly upward, so if you had some kind of, some kind of thing that you wanted to rotate, and you pull directly 90 degrees from the position vector, that is going to give you the most rotating power possible. So that's that is how this equation works. All right. Now you can think of it when you're drawing your vectors in actually 3 different ways. You can say, okay, I'm going to go R cross F. All right. So, and you could say, okay, well, that's going to be the magnitude of the position vector. And then, which force is actually causing the rotating? Well, you could divide your force into 2 components, find the component that's doing the rotating, and say, oh, that's going to be R. Come on, there we go. That's going to be R times F sine of theta times that component, and that is going to give you the size of the torque. Or you could look at it and say, okay, this is my position vector, this is my force, but when I cross the two, my tails have to be together, so I'm just going to move my position vector to right here so that the tails of my position vector is with the tail of the force vector. And so I would multiply the magnitude of my position vector times the magnitude of my force, and then just simply look at the angle between them, and in this case it's phi, and plug that in there to get the size of my torque. Oops. Kind of did a pi there, not pi, torque. All right. Now, in later problems, it is going to be easier to say, all right, I have this vector and this vector, and since we know that the sine of theta is equal to the sine of phi, which you could prove to yourself, the sine of supplementary angles is equal, then you could do it where you just say the magnitude of R times the magnitude of F is equal to the sine of theta as well, and get the same value for torque. Torque is a vector, however, so so you are going to want to cross your R into your F to get the clockwise or counterclockwise, or you simply are going to look at your object and say, this force, and I'm going to use a different, let's use black, this force is going to cause this wrench to move in a counterclockwise direction. So that in counterclockwise is associated with positive, and in this case it's going to be out of the page. All right. In order to get, as if this was a wrench, in order to get, so if I were to put the force this way, then here's my position vector R, but I have to have the tails together, so I'm going to redraw it as R this way. Then they would cross into each other in the clockwise direction, but easier yet, the force would turn the wrench in a clockwise direction. Clockwise means negative, and that would be going into the page. All right. Now, the last, torques are difficult to visualize, so if you're, it takes a little while to absorb this. Now, the last thing, and it's easy and confusing all at the same time. Yikes. The question is, what are the units of torque? All right, well, how do you figure out units? Well, we know that torque, all right, I am sorry, something weird, some weirdness happened there. Okay, come on, baby, here we go. Torque equals R cross F, right? Okay, so what are the units of R? Well, R is position, so that would be M, meters. And force, well, force is in newtons. Oh, wait a minute, that would be a Newton meter. But wait a minute, where did you hear the units of a Newton meter somewhere before? A little thing called work, didn't you? Force times distance. Force is newtons, distance is meters. All right, well, they do have the same units, but a Newton meter here is not equal to a joule. All right, so it is not equal to, it's not like the units of energy, not equal to that at all. Just so happens that it's the same units, but not equal to joules. All right, so you could never simplify this. And please do not simplify this to a joule, because a torque is a vector. Joules describe energy. It's a unit of measurement for energy, and that is not a vector. You'll get this. You'll get this. It just takes a little while to absorb. Okay, so in review, a torque is required to rotate an object. A torque is measured in Newton meters, but this is not a Newton meter that is equal to a joule, so don't think that torque is energy. Torque is a vector, so you need to indicate direction. Now, to understand why we said that torque is into the page and out of the page and all that stuff, you need to understand how the right-hand rule works. So, if you are in a physics class that needs to know that, then please consider watching Using Torque to Explain the Right-Hand Rule video. And as always, remember, hardworking scholars can do anything.